So much, Chris, for the very nice introduction. And let me start again by sharing my screen.
That looks perfect.
Yeah. Yeah, so as Chris said, I mean, today we will, in this lecture, the first lecture of today, we'll talk a bit about the training algorithm, the optimization part. And let me remind you what we did yesterday. So we first looked in very general terms at neural networks, identified key mathematical directions, which are interesting to pursue, both for mathematics for deep learning as well as deep learning for mathematics. And the 10 lectures will cover this to some extent. And then we also took a look at, because deep learning contains the name learning, so at statistical learning theory. And from this theory, three main of those directions actually also arose in a very natural manner, which was the approximation question, approximation by the hypothesis class, then the training, so the optimization part, and the generalization. And so yesterday, then in the second lecture, we talked about expressivity, so approximation part, and today we will first in this lecture talk about the optimization part, the training part, and then later on today in the second lecture of today, so in the fourth lecture, we'll talk about the generalization part. What I would like to do in the first is just to give a very brief recap of statistical learning theory, because I assume, this was very quick, and so we will use some of the notions today, and so therefore I think it's good to do a brief recap so that everybody can remember what our notation was, and then also follow the subsequent part in a much better way. So the idea, about learning, which we discussed yesterday, was this was a very high-level viewpoint. We had three measurable spaces. Later on, Z was always X times Y. We had our data in Z, and we had a loss function which did the following. It mapped a function, a measurable function from X to Y, times our data to R. Yeah? So it measured in some sense how good, let's say, this function fit the data. What was crucial was that certainly we cannot deal with all measurable functions. We need to take a subset that was called a hypothesis set. And the main goal of the learning algorithm was then to take data and map it into this hypothesis set. So we map our training data to a model, and the requirements were that this model performs well on the training data and also on unseen data. Yeah, so this was the generalization part, and so the performance was certainly then measured by this loss function. Then we delved a bit more deeply into the specifics. So we look at prediction tests. So as I said, Z will be X times Y. So these slides you have already seen. I just want to bring it back into your mind. We have training data Xi, Yi, and regression and classification tests are the two main tasks we are looking at. So it's very canonical loss functions. Here's the square loss, and here the 0, 1 loss. The hypothesis set were neural networks. So let me also remind you of the notation which we introduced for that. We always distinguish the architecture from the realization of the neural network. So the architecture corresponded to a vector n, which indicated how many neurons there are in each layer, and an activation function rho. And the realization was then a function which mapped a point from the input space and a parameter, an element of the parameter space, to, well, some value, for instance, in R. And so P of n was the number of parameters, and this corresponded to, well, all these, let's say, weight matrices and biases, how many entries they all have added up, because that's what we train. And again, let me remind you, the hypothesis class was denoted by FA for the regression test and FA sign for classification. And then we identified a very specific learning algorithm which minimizes the empirical risk, which is what people typically also use This was the definition. So the risk just takes into account the training data, nothing more. Which you see here, we denoted it by R hat S, and the associated algorithm then minimized this risk, and the minimizer was called FS hat. Then we also, to define generalization, we went to the, let's say, continuous world. We went beyond the samples and the test training data which we have at hand. So we formulated in a continuous way. The risk now is, again, the loss function, but now integrated over this measure. And the risk of the model is then given in this map. So introducing this continuous version, one could now identify or define generalization. And first, I mean, so these were also notations which we also introduced, the minimization, the minimizer of the risk. The function itself is f star, called the base optimal function. R star was the base risk, so the minimal one which one can achieve if one knows everything, not just the training samples, but the distribution as well. And so this f star had some closed form solutions, which we also took a look at. And then this was the main slide, which told us how we can distribute, not distribute, but partition the error we're interested in into three components, namely the approximation component, which just looks at what happens if I now restrict to the hypothesis class, the optimization component, which deals mainly with the algorithm itself. You see, it's the optimization error, studies here the empirical risk in F and FS hat, and then the generalization error, which looks at what happens if I go from the empirical risk to the true risk. So if I, let's say, go beyond the training sample setting. And so yesterday we already dealt with, to some extent, with the approximation error, showed a bit, I mean, some methods how you can control that, how you can bound it. We also saw that to some extent neural networks are as good as previous approximation methods. So in that sense, not that surprising that they're also very powerful, for instance, for problems like inverse problems. And today we will now, in this talk, focus on the optimization error. Okay, so as I said, I mean, so this error, which we now focus on, is mainly influenced by the numerical algorithm. So this, depending on the algorithm here, we will always use basically gradient type methods, but certainly you can also imagine any other type of algorithm. And so this would then always have direct impact on the optimization procedure. And again, as I already said on the previous slides, we will focus here as well on the empirical risk. So the algorithm aims to minimize the empirical risk. Yeah, but also there, I mean, one can think of other settings, but this is the very standard setting which we will analyze. Again, the empirical risk here, we have the loss function, we have F, we have our training samples, and we take the average loss over the training samples. Now, to minimize this, the most common one, I mean, the most common approach are gradient-based methods. So what do gradient-based methods in general do? Well, I mean, it's a very simple philosophy. So if you're on a mountain, how do you get to the valley? Well, I mean, one idea is certainly to always follow the steepest descent. And so, I mean, these gradient-based methods look basically at the part where, let's say, the gradient is the largest, and then follow this path in steps. And so this also relates to the step size. So it's an iterative algorithm, which finds a path, basically, hopefully, to a minimum, hopefully to a global minimum, but maybe also only a local. So it paths proceeds along this so-called loss landscape. Yeah, so that's the general philosophy of gradient type methods. Always follow the gradient, and then hopefully one does not end up in some, let's say, other local minima where one is trapped, but hopefully one reaches the global minimum. So sorry. Yeah, exactly. So what are the key questions? The key questions are certainly how fast does the algorithm converge. So this depends on a lot of, certainly on the loss landscape. It depends also on the step size you choose and on various other ingredients. Then it could be that the loss function is not convex, so there could be also a lot of different type of local minima. So one could end up in a local minimum and don't get out there. But hopefully it will be a good one, whatever good means at this point. So does it converge? So to what does it converge? And maybe also what are good starting values, because at some point we need to start the algorithm. And as I said, I mean, the method of choice in deep learning traditionally is to use what's called stochastic gradient descent. So what is stochastic gradient descent? So this is the algorithm. It's actually not that new, as you see. So the input is you have a differentiable function, little r. As I said, one needs to choose also the step sizes one want to use, how far you go for each step when you follow the gradient. And you have a random variable with which you start. The output is a sequence of random variables, which basically give you then the path one has to follow. And as I also said, it's an iterative procedure. So you always have an update step where, as you see here, you have the previous theta k minus 1, you update it, and then you get the next one. So the updating is set somehow in the direction of the gradient. And so in the updating step, you see here also the step size, which tells you how far, in a sense, you go. And so here this dk is defined as here a random variable because we are in the stochastic gradient descent setting. In gradient descent, it's deterministic. So there it's just the gradient of r evaluated in your previous point. Here we have the stochasticity involved. And so this is how you choose this dk. So you choose it so that it's that the expected value of dk, if you know theta k minus 1 is this gradient. Okay, so that's basically the core algorithm. And before we now look at it in a bit more detail, let me also show you this picture, which I think maybe shows a bit the difference also to gradient descent. So see, gradient descent, as I already said, we have here our, let's say, loss landscape or landscape over which we minimize. We start somewhere, and then, well, I mean, we follow the gradient and we end up maybe here. If we start here, if we start here, we end up here. Yeah, so it's, you see, it's also very sensitively dependent on where you start. But the path looks very straight. You always follow the gradient in a very conscious manner and in a deterministic manner. So this is gradient descent. And so you see, I mean, you could also end up in the maybe wrong minimum. Stochastic gradient descent is much more erratic because you have this stochasticity involved there. And so what could happen is, you see, you start here, maybe. So one time, if you start here, you can end up in this local minimum. But I mean, then if you, let's say, have a different realization of everything, you end up in this minimum. Yeah, so this shows, let's say, how sensible that is, but it also shows how difficult it is to actually analyze. I mean, there are some interesting results, but I mean, a full understanding is still not reached at this point. But I hope this picture shows a bit also the difference. What the advantage is also of this erratic path is that because of that, as you see, I mean, even if you start maybe at a wrong position where gradient descent would end up here, this could still end up in a global minimum because it wriggles so much. Okay, so we minimize the empirical loss. So our function little r is the empirical loss evaluated at the realization of the neural network. Yeah, and so let me remind you, R is now in Rpn, and Pn was the number of parameters of my neural network. So that's the function R. And now, I already said, I think in the first lecture, that typically we have millions of training samples. And certainly you don't want to compute a million gradients. Because of that, what one chooses is a so-called mini batch. So we don't look at all training data, but each time for each iteration, we look at a selection of that. So that's a so-called mini batch. So it has a certain size, M prime, and these samples are not chosen randomly from the training data. And the intuition somehow is that then if you have this random collection, that on average, you get, let's say, close to the average gradient to some extent. Okay, so then the updating step looks like this. So you see it's similar to before. So now we have here the gradient here of the loss function. We have here the realization of the neural network evaluated in my previous, let's say, random variable. We sum now over the mini batch, where certainly, I mean, the number of elements in the mini batch is less or equal than the number of training samples, usually much lower, maybe just M prime might be just 100 if M is a million. And then you have here the step size involved, so which is here typically called the learning rate. Okay, so that's the algorithm. And then after k steps, we get our model, the risk of our model. And so you see what we do. We have our last random variable here from the k step. We take a realization of that. And this gives me now my realization of the neural network, which are defined by fs. And so this is now my trained, the realization of my trained neural network. Okay. So that's the approach. And certainly, I mean, there are convergence results, but, and this looks actually like a really nice result. It's an impressive result. The caveat I already marked in red. Okay, but let's take a look first at this result. So we have here our function R, which is differentiable and convex. Then we have our output of stochastic gradient descent, these random variables with some initialization, with some step sizes. And we have also these random variables dk, which we also saw in the algorithm. And then this is the estimate. So this theta star is the minimal theta possible. So that's what we aim for. And so what this says is that the expected value of R evaluated in this theta bar, and you see theta bar is now here the mean of these theta k's. So this error is bounded above by 1 over the square root of k. And so this shows that if I increase the number of steps, so if I let k go to infinity, then this converges to 0. So that's a nice convergence result, which even gives the rate of convergence. It's a powerful result, but it has a small problem because it requires convexity. So if R is not convex, I mean, then basically all odds are off. So then stochastic gradient descent may converge to something else, so some local, non-global minimum. Yeah, so the message is stochastic gradient descent has been, I mean, they're very nice results to analyze it, but most of those results require convexity. Our problem is that the empirical risk is severely non-convex. So it may exhibit a lot of, let's say, bad ingredients. Yeah, some saddle points, some suboptimal local minima, some wide flat areas where the gradient is small, so where it's very slow to proceed, and so on. Yeah, so it can be an extremely complicated and very unfortunate landscape where you could get trapped also in some local minima, which might not be that good for generalization. On the other hand, if you look at applications, stochastic gradient descent is extremely successful. And that's certainly, I mean, a mystery. So what one could expect is that the trajectory of this optimization procedure somehow, for some reason, misses these suboptimal critical points. And it might also seem to also miss areas like these white flag areas where you have very slow convergence. Yeah, and so, I mean, this field of optimization sets out to unravel this mystery. And there are certainly various paths you can take now to attack this, and I would like to show you a couple of those, not all in full depth, but so that you get an idea of what, let's say, approaches are and could be to tackle this challenge. Okay. So, I mean, certainly the first idea is to analyze the loss landscape. So again, I mean, this is our neural network, the realization of our neural network with our training data, and the graph of this R of theta, which I said is here the empirical risk valued in the neural network, is then called the loss landscape. So that's what one needs to analyze. And again, I mean, so this is the picture I showed, a very benign landscape, which is usually much more complicated. So that's the task, to analyze the loss landscape. And so here you see also other pictures. What you see here is that also if you zoom in, things can become really complicated. So here it looks quite nice, but then, so this is a zoom up of this area. This is another zoom up of this area. And again, you zoom in. So you see how complicated things can be. Yeah, and so this is even, from my, if I remember correctly, a very easy neural network, the loss landscape. Okay, so one approach, one approach is to analyze the path to the parameter space. So, I mean, this seems to be something very natural, because you saw, I mean, the gradient descent algorithms follow a certain path. And so here, one idea is to look through paths, also through the parameter space, where the empirical risks are monotone. Yeah, because what you would like to analyze is whether there are maybe unfortunate minima where things can get trapped, or looking at paths which in any case converge to a global minimum. So in that sense, one can look at, and that's one approach people take, look at the parameter space, look at the resulting empirical risk to those, and then look at, for those paths where these empirical risks are monotone, non-increasing, and hopefully converging to a global minimum. So this requires a lot of geometry, also sometimes differential geometry, tools from differential geometry come into play there. And there are various results in this respect. So here are two of those where people looked, I mean, the group around John Brunner looked at so-called spurious valleys, which are, as it says here, connected components of level sets that do not include a global minimum. So these are, in some sense, bad values where the paths can get trapped. And so why are these ideas? I mean, they could show in certain cases that there are such spurious valleys, or that they are not present. Yeah, so that's a very geometric approach, looking at the geometry of this landscape using tools of also, for instance, differential geometry. A very different approach comes from mathematical physics. So mathematical physics has a lot of very powerful tools, and for instance, also what's called the spin glass model. And so so-called Hamiltonian, which is a certain operator related to that, is a random function on the sphere. And what these colleagues showed was that the loss function of a neural network with random input can be considered as this object, as this Hamiltonian of a spin glass model, which is very nice, because then all these powerful tools from mathematical physics you can actually translate to analyzing the loss of a neural network with random inputs and analyzing, in that sense, the loss landscape. And so that way, I mean, what people then do in this respect is they look at a set of critical points, aiming to analyze how bad the loss landscape can be. And one can associate it, a so-called index, with the Hamiltonian, which gives then reveals information about the relative number of directions where the loss landscape has negative curvature. And in that sense, one can look at the critical points and analyze the relevance of the critical points for the training procedure. For instance, here, as it says, I mean, if you are very far away from the optimal loss and the critical points become unstable, so that gives indications that you are maybe not in a good area. And then the question is, I mean, can you characterize when this can happen through using ideas from mathematical physics? And the same also with the relation between local and global minima. So this, again, I mean, it's one of these instances which I very much like, where a connection is drawn between deep learning and one particular area in mathematics where now the powerful tools are carried over. So then there is something which is called lazy training. And lazy training is an effect which one observes many times. And it also gives rise to analyzing what happens during the training. We will also now see some ingredients which we will then revisit when we look at generalization. So what happens is the following, as you see here. So these are the changes of the weights, and these are the steps of the algorithm. And as you see during the steps, first, I mean, there's quite a change in the weights, in the biases, so in the parameters which you train, but then they stay almost constant and don't change much. Yeah, and so this is what one observes numerically also in highly overparameterized neural networks, that then, I mean, after this very initial phase, I mean, the weights and biases are almost constant. Still, I mean, you see here the descent steps again, I mean, the loss still decays, although, I mean, the weights and biases are almost constant. And so this is a result of the different neural networks. You see here the color coding relates to how many neurons the network has and what is tracked. Okay, so that's an interesting effect, which one can actually also analyze, and which one can, to some extent, even prove. And I would like to give you a bit of insight into that, so that you see how, on a high level, how one can. So let's assume we have a very easy neural network model. It's not as easy as a linear model, but I mean, it's an easy network with one hidden layer. We have our training data, as usual, xi, yi. We have the empirical risk, which we are also now familiar with. And we have an initialization of the parameters where these two components follow normal distributions. Okay, so that's the setting. And now one would like to analyze the gradient of R over this starting point. So that's now the starting point from which we would like to start our path, hopefully towards a good minimum. So what one can do is, well, I mean, we need to analyze the norm of it. So we can just first use how the empirical risk is defined. We pull also the gradient in here. We write this out, which gives this formula. And what is now interesting is this kernel which appears here. So this k bar theta is written down here. And so this kernel will appear at certain instances. It's also in the generalization part, because it's very useful for certain proof techniques. Yeah, so you see here, I mean, you have here the difference between the realization of the neural network and the labels, and the same here. And then you have here this random Rm times n value to kernel. Okay, so in our case, because we have this very easy situation, we can explicitly compute what this is. So it's just the activation function applied to these inner products. So the kernel has now this explicit form. So it's the sum over vk transpose, and the vk's have this shape related to this. Good. Okay, so now, I mean, let's carry that over to the next slide. This kernel has nice properties. So for sufficiently large n, with high probability, this is a positive definite kernel, and the smallest eigenvalue scales linearly with n. So yeah, so let's go back to remind us what the ingredients were. So you see the n here is the number of parameters, so the width of the neural network. M is the number of training data. Okay, so that's a nice property. You can prove this. And using this property, one can now lower bound this the absolute value of this gradient by this part, which we already saw before, but now we can use that this kernel has the smallest eigenvalue, and we can then use this eigenvalue scales linearly with n, which gives us this asymptotic lower bound. Yeah, and again, I mean, this is the width of the network. This is the number of training samples. Okay, so let's carry this over. We can then analyze what happens if we deviate a bit from this initialization. Yeah, because I mean, then certainly, I mean, as we move through the landscape, I mean, we need to analyze what happens if we change this slightly. And so one can do a computation, again, which I don't want to go too much into the details there, using, again, the positive definiteness to get this lower bound. And so you see here, this relates to what we already had here. So now this shows that, in fact, you can deviate from the initialization by some value in B10, which is the ball of radius 1 around 0, and you get here the similar lower bound as well. Now, using this, one can show that for sufficiently small step sizes, and where, let's say, I have a relation of the case initialization of the case parameters to my initial parameters of 1, we get a relation of this type. So here you see the empirical risk in theta k plus 1. This, due to the update rule, behaves approximately as this risk of theta k, the previous one, minus the step size times the absolute value. We then use this relation, which we computed. You see the n over m appearing here, and r of theta k, and we can then also estimate it in this way, again, by the previous relation, and ending up, so if we combine these two terms, we get something of the type. So what does it mean? It means the norm of the gradient of r evaluated in the case parameter, random variables for the parameter, can be lower bounded by n over m times the empirical risk of theta k. One can go then one step further to get also a related relation. Before we had the other relation, one can also prove that and conclude from that, using previous considerations, that in some sense the step sizes are bounded, and also the overall error behaves or decays exponentially. So from this computation, and the main point where I wanted to show it to you also was that, I mean, this kernel is in a sense essential, and we will see how useful it is later on as well. But so here, I mean, the arguments are not that complicated to some extent, but still you can prove. And so this was done by these colleagues, these two results. I mean, gradient descent converges with an exponential rate to an arbitrarily small empirical risk if the width is sufficiently large. So this n, you saw how it appeared, and the n was also related to the kernel, because, as we said, I mean, the smallest eigenvalue scale linearly with the width. And moreover, the iterates stay in a small fixed neighborhood of the initialization during the training. Now, so these two things which we saw in these numerical example can be also rigorously proven, which is actually really nice. Yeah, so I mean, there are certainly much more details, but I wanted to just give you here the main message of the result proven there. And so this is typically related to lazy training, meaning that the parameters change only very slowly and stay in a neighborhood, which then also to some extent makes the analysis maybe a bit easier. Okay, so this explains also one of these phenomena which one observes numerically. Good. So, and there are, I mean, many types of these approaches. There's a very new, I think, very exciting approach which considers part of the training. Yeah, and so this is a general trend, as far as I see it, that also sometimes not the entire training procedure is considered, but only parts of it, and sometimes in very special situations. So here in this approach, which is called neural collapse, one part of the training is considered, and what is considered is this last part. Yeah, so typically in a neural network, what one observes is that we have here the network which generates the features, the feature vectors, and then afterwards we might just put a linear classifier. And so then, I mean, the question is, and what in this work was studied, how this relates, how the features relate then in that sense then later on to this linear classifier. Because what could be, again, I mean, numerically observed is that, I mean, these features then to some extent also cluster around their class means. And so something very geometric seemed to be happening there, which could then also to some extent rigorously. Yeah, so this is now again, I mean, back to classification problem. And yeah, so we will denote these feature vectors by H. So that's here what comes out of this first part of the neural network, and then afterwards we have the linear classifier. So there we will denote the matrix related to this by W and the bias term by W. Okay, so and the question is now, I mean, what happens basically during training just in this last part? For the geometry, I would like to first introduce one notion, because that's actually the geometry which is then behind everything, which is quite nice. So this comes from the area of frame theory, which is an area of functional analysis in mathematics, and the notion of an equiangular tight frame. So if you're familiar with optimal packings of lines in Euclidean space, you have a couple of lines, you want to span the space in an optimal manner, then there's a close relation to this equiangular tight frame. So it's very geometric, but I mean the precise definition you see here. So it's a family of vectors in RD, which is normalized, where the angle between each pair is constant. And then you also have some sort of reconstruction formula, like you would expect, for instance, for an orthonormal basis. If you have an orthonormal basis, you would not have, let's say this, but here you have this reconstruction formula with this scaling factor. Now, so that's an equiangular tight frame. The easiest equiangular tight frame is a vector, 3 vectors in R2, which is, yeah, I didn't draw it here, but I mean, it looks like this. So you have 1 vector here, 1 vector here, and 1 vector here. So this is the best with 3 vectors, how you can span out. Okay, so that's an equiangular tight frame, a very geometric object, a family of vectors which basically span the space in an optimal way. Good. So now let's look at this neural collapse phenomenon, and let's assume we have three classes. And so what you see here are the features of the training samples. Yeah, so these vectors H, which come out of the first part of the neural network. So these are the features, and you see the color coding related to the different classes. And now the question is, I mean, what happens during training? And what you observe is that these feature vectors of the training samples start to cluster, and they start to cluster around the class mean. So you see the definition of the class mean here. And this is called, in this approach, variability collapse. So all of those, the features of the training samples converge to their specific class mean within the class. Maybe not that surprising. I mean, you would to some extent expect something like that, because that's a reasonable thing to do, but I think it's nice that this can be now also rigorously analyzed. So then if you go one step further in the limit, you will get a picture like this. Yeah, so then all of the features have already accumulated here, here, and here. And yeah, so these are again the class means, but what is now very nice to see is the structure of this. Yeah, so because you see here now, this is one of these equiangular tight frames. And so again, I mean, the definition is here. So the H here in the middle is the global mean. And so what you see here is that the angles between each pair is each time the same. Yeah, so these vectors are always Hn minus H. We saw that in the definition of the equiangular tight frame, and then also that these norms converge to each other. Yeah, so in that sense, I mean, the training aims to converge to a very geometric object, which then spans the space in an optimal manner to exhaust the space. And you see also the advantage, because now, I mean, these training samples are basically as far away as possible from each other. Yeah, so then therefore it's a very useful or sensible way to do, which happens there during the training. And what one also sees is that, in fact, I mean, these class mean also converge to the linear classifier. So the linear classifier were these WNs. Remember, this was this matrix which gave us the last step of the neural network. So that's what's called their duality. And in effect, I mean, then if you look at the overall neural network classifier, what happens is it actually chooses each time the nearest class center. So there are also other algorithms which just do this, but this is in some sense what then the overall classifier aims for. So one can really characterize in that sense what the neural network classifier does. Yeah, so this is another picture which is also taken from the paper, and so this is stage 1, 2, 3, 4. What you see here is, I mean, the green dots are later on, I mean, the equiangular tight frame. The red structures here is the linear classifier. The blue are the class means. So the blue balls with a stick to it, these are the class means, and these blue balls or these blue spheres which you see floating around everywhere, I mean, these are the feature vectors from the training samples. And now what you see overall during the training steps, I mean, they start to accumulate here more and more. And moreover, the class means start to converge to the linear classifier and also to a geometric structure which spans the space in an optimal manner. Yeah, so in this phase of the training, the features collapse to a equiangular tight frame, and therefore, I mean, what happens in the classification of that last step is nearest class center decision rule. And there are various additional works which study this with additional constraints and so on. But I mean, this is now, I think, one new interesting contribution to this area. But then one can say, or one can also ask the question, is training really necessary? And in the last minutes, I would like to show you or discuss with you to which extent this is actually true. Because there's another very interesting approach, which shows that maybe, yeah, to some extent, one can also pre-select the parameters in a meaningful manner. Now, this goes into the direction of convolutional neural networks. Since we haven't defined that formally, let me just use this slide to introduce it. A convolutional neural network, which was already part of one question which was asked yesterday, is a specific structure. It also has certainly it has a step where affine maps are applied, activation. Here there's an additional part which is called pooling, and these affine maps, there are to some extent convolutions. So these are networks which are typically used, for instance, for image processing, because there, if you, for instance, would like to classify whether there's an object in the image, it doesn't really matter where it is. So basically, I mean, that makes the usage of convolutions very attractive. Yeah, so in that sense, I mean, these networks do convolutions and ReLU, but then to reduce the size of the layer, they pool, meaning they reduce the size in a meaningful manner, and then again, convolution, ReLU, and another pooling layer. So that's the architecture of these convolutional neural networks. And there was a very interesting idea by Stéphane Malard. You see, it's already very old in this area. 2014 is almost ancient, but still, I think it's a very interesting idea. So I would like to also bring it up here. He introduced a special convolutional neural network, which he called the scattering transform. And it is not trained, it uses predefined filters, namely wavelet filters. Remember, yesterday we already introduced wavelets. This is a representation system with certain nice properties. And what he could show is that the scattering transforms in certain instances performs sometimes close to trained neural networks. Certainly, I mean, you can analyze it much more rigorously because you don't train. And also there's a nice continuous as well as discrete theory. So how do they look like? So the main idea of the scattering networks are you have convolutions with, as you see here, with wavelets in a certain manner, and the activation function is then just the absolute value. Yeah, so here not a ReLU is used, but the absolute value. And so you see here, I mean, you convolve your F with different wavelets, you take the absolute value, again, you convolve it with wavelets, again, you take the absolute value, and so on. Yeah, but what he also uses is that in each layer of these layers, he also has, let's say, an additional output of the network, which is also used for in the feature vector in the end. And also one has to say, because each time you convolve with each wavelets, I mean, you cannot compute many layers because the number of neurons in each layer goes up exponentially. Still, I mean, I think it's a very interesting approach. So this is a short-term notation for that. Again, you see here now this convolution with the wavelets is just indicated by the parameters of the wavelets. And one can also prove nice results in this respect. Let me maybe the last minutes just show you a bit of what could be proven that also relates to maybe tomorrow to robustness questions. So here is a more precise definition of a scattering transform, but still I don't want to go too much into the details. But let me say, you see here again the wavelets. for these results, we need the wavelets to satisfy certain conditions. Yeah, like a Bessel equation. We have the absolute value as rectifiable as the activation function. And then, as you can see from the previous image, you can take now different paths to this neural network. And each path follows certain parameters of the wavelets. So basically, you can characterize each path by the sequence of parameters of the wavelets it follows. And so then, I mean, so this is the scattering transform in the end. So F is mapped to this this object, which now collected everything which comes out of the neural network in the different layers and in the end. So what one can prove is, for instance, that this scattering transform is translation invariant, which is a nice property. You see, it doesn't matter if I translate my input, for instance, image, or if I then translate the feature vector, which I get out. That's a nice property. But even more, what I think is maybe even more interesting, I mean, one can prove some stability. Yeah, so one can prove. Let's take a look here first. So you have here the scattering transform, you have here your input. And what you do now is you deform your input. And you deform it by an operator which looks like this. So you can imagine you deform it in a certain manner. The deformation itself, the theta, is controlled. And also its derivative is controlled. But still, I mean, you can show that the feature vectors are to some extent stable under deformation. And you can get a rigorous upper bound for that. So I think it's an interesting, very interesting idea. It shows that to some extent using sophisticated patterns in your filters, in your parameters of the neural network, choosing them deterministically, you can get sometimes even close to fully trained neural networks. Okay, so let me conclude. Yeah, so we looked at optimization, training algorithms. Stochastic gradient descent is a very typical choice in this respect. There are interesting and strong results for stochastic gradient descent. Unfortunately, they require convexity typically. Here, if we look at empirical risk minimization, that leads us to severe non-convexity. Still, the algorithms perform really well. So the question is why are good local minima found? And there are various approaches, some also which I didn't have time to mention here. So we looked at a couple of approaches which aim to analyze the loss landscape, for instance, by geometric means, also by methods of mathematical physics. We looked at this phenomena of lazy training, which one observes numerically that the parameters then change very slowly during the training phase, and one could, we saw, rigorously even analyze it. We also looked at what's called now neural collapse, so that for classification in the last part of the neural network, something also very dramatic happens, and also something very smart, so that the different classes are basically optimally separated in space automatically by the training algorithm. And the last question I then also ask is training necessary? How far can one get with, let's say, predefined parameters? And that was introduced and discussed in this approach from the scattering transform by Stéphane Mallat, where he used very specific parameters, namely coming from the wavelet transform, and to some extent sometimes got quite close to true training algorithms. And with this, I'd like to conclude, and thanks for your attention.
Well, thank you very much, Gitta. So as before, we're going to have a look at questions both from the floor and in the chat. So we'll kick off with questions from the floor. Do we have any questions or comments? Right. Would you'd like to say your name and your question?
Hi, I'm Anshul Thakur. I'm from University of Oxford. My question is regarding lazy training. So is lazy training also related to the fact that when we are looking at the over-parameterized neural networks, only a subset of parameters are kind of changed during the training. So if you look at the deviation of the parameters during the initial stages and the final stages of the training, only a few parameters will be changed and rest are kind of in the same neighborhood. So is that due to lazy training, or lazy training is entirely different from it?
No, so for lazy training, as I said, is that, I mean, the parameters overall change only slightly. So what you mention is, I presume, a phenomenon also of that.
Okay,
so,
thank you.
Yeah.
Thank you.
Thank you. Any other questions from the floor?
Hi, Quaker Abraham. So I had a bit of confusion with the lazy training as well. So the two kind of things in the theorem you showed, that it converges exponentially fast to an arbitrarily small empirical risk, and also it doesn't move very far from where it starts. I didn't quite see how they're compatible.
Well, I mean, so this is in the very high dimensional regime. Yeah, so the highly over-parameterized regime. So you have millions of parameters, and certainly each single one of the parameters might change only not that much, but overall, since you have that many parameters, I mean, overall, you can get then a good, let's say, convergence rate. Yeah, so
there's always something near where you start that does well.
Sorry?
So there's always something near where you start that does well.
To a certain extent, yeah.
Oh, thank you.
Thank you, Kwaku. Any other questions from the floor? We have quite a few questions in the chat. I don't know if you can have a look at the chat, Gitta. So if we go to the bottom, we have one from Masha Yousefi. How can we solve the problem mentioned with lazy training? It seems this type of stagnation for updating networks parameters happens regardless of the optimizer. It happens even with a second order optimizer.
Mm-hmm. Yeah, I mean, I wish I could answer that question. I actually, yeah, I don't know. I think that's a question which is, I mean, certainly a very important question, but I unfortunately cannot comment on how that could be solved. I mean, I think if someone, yeah.
Thank you. Well, here's the next one from Cedric. Doesn't say who it is. Might be Cedric Villani, who knows. Excuse me, I got a question. I can't wrap my head around the definition of a deformation. Are they conformal maps or diffeomorphisms?
They are diffeomorphisms.
Okay, thank you. From Zidak Pal Singh, does this phenomena of neural collapse require a certain minimum amount of information of width or depth, or is it rather universal?
Yeah, I would need to check in detail, but I mean, so from what I remember, I think it's rather universal.
Rather universal.
Yeah.
Thank you. Don't think that's relevant.
So I think the other questions are not related to the talk directly. It's a Word document.
Yeah. Okay. I think they're just, yeah. Well, thank you for putting that. Oh, didn't mean to do that. Where are we? I've lost you. Get rid of that. Yeah, back to you. So are there any other more questions from anyone? Well, then it remains for me to thank Gitta very much for this presentation. The next thing we're going to do is, I believe we're going to have our photographs taken, even though you can't